Okay, I'd like us to run through a couple point charge electric potential problems just to kind of show you how they work. And I think that they're really simple. And after figuring out electric field due to point charges, this should not be very much for you to worry about. But let's go through them just so that it's clear. So in this case here, you were given 2 point charges. They're identical point charges. They're spaced apart by a distance d here. We're assuming that potential equals 0 at infinity. We have to do this. This is really important. If you're wondering why this always comes up here, this assuming potential equals 0 at infinity, because we have to set where the 0 of our elevation is. Remember, we're considering this to be like elevation. So elevation, when you think about it in the earth, really a lot of times when we discuss elevation, it's always with respect to sea level. So sea level is kind of like our artificial zero elevation on the earth. So we have to choose it somewhere, right? We have to choose a reference zero somewhere. And what we do with electric potential is we choose it at infinity. Your textbook goes into that, so I'm not going to go into it anymore here, but I wanted to remind you that that has to be there and that it's important. Okay, so let's go ahead and start this problem. The first thing that they're asking for here in part A is to find the potential at point C. So we just are using the point charge equation for potential here, KQ over R. So that's what's relevant. Potential, the point charge equation, simply KQ over R, and we're interested in the potential at point C. So that means that we need to get our hands on these distances. We need the R values, right? And so they're both going to be the same for that. It's that hypotenuse there, that R value. And if you do that math, then you get that R is equal to D over root 2. So that's our R value. So yeah, if I want to find then the potential at point C, I sum up the potentials from the charges that contribute to it. So that's just going to be K times positive Q over R, which is D over root 2. So I'm going to just pop that root 2 up in the numerator and say for the left charge, and then I'm going to consider the right charge. And it's going to contribute in exactly the same way, isn't it? It's the exact same charge, positive Q, and it's the exact same distance away, D over root 2. So a couple things. First of all, you might be like, yeah, it's a different angles. That doesn't matter. Of course, potential is a scalar. That doesn't matter. It's scalar. Your other question might be, why is Stephanie putting in these signs, the positive signs here? Because even though potential is scalar, it is signed. So positive charges contribute positive potential, negative charges contribute negative potential. So just as a workflow for myself, when I do electric potential problems, I routinely will include the charge just to remind myself that the charge needs to be included. Okay, so if we sum these two things here, v sub c, then we'll get 2 root 2 kq over d, and that's positive quantity. So potential being positive means that it is an elevation that's higher than the 0. Okay, so that's part A. Part B asks us for the work necessary to bring in a third charge to point C from infinity. So it is going to take some work to do that. Like imagine yourself doing that, bringing that third charge in. It does not want to be brought in because it's repelling from the two positive charges that are already in that space. So in other words, when you're bringing that charge in, you're bringing it what I would call uphill, right? So it necessitates positive work from you, an external force, yeah, positive work from you to bring it into point C. The field itself will be doing negative work, Remember work, yeah? So the field itself will be doing negative work as the force exerted by the field will be in opposition to the displacement of the particle. But the force that you exert will be in the same direction as the displacement of the particle. So the work that you are doing will be positive. So whenever you do work, whenever you're thinking about work, always a good first place to stop is, am I expecting this work to be positive or negative? In this case, they're asking for the external work necessary for you to do that. Okay. So to find that work in this equation right here, notice that you're told in that equation that work is equal to the negative change in electric potential energy. This is defined as the work done by the field. We are talking about the work done by you, right? So the work done by you is going to be negative of the work done by the field for the reasons that we just went through there. What that means is the work done by you is going to be equal to the change in electric potential energy. Great. So we can figure that out. The change in electric potential energy. One of the equations that I neglected to write down here is that electric potential energy equation here, which is just going to be K Q1 Q2 over R squared. I'm sorry, over R. Your textbook does a good job with um, going through this equation and the derivation and stuff like that. So if you missed that section, go back and look at it. So what I need to consider here is I need to consider the change in potential energy between each pair. So notice there's a Q1 and Q2, and that's because just one particle by itself has no potential energy. It's not interacting with anything. There are no forces. So you need to consider the particles pairwise. So say, I don't know, let me call this particle over here on the left A and the one on the right B or something, and then we can kind of keep track of that. So then the work that you would do, the work that you are doing, is just going to be a sum of the two different pairs. So that'll be K times, um, let's call all the charges have positive Q, right? All the charges have positive Q. So positive Q over, and then remember we're bringing it into point C. So the distance between the charges A and C. So let me start by doing A and C here. That distance is going to be D over root 2. So D, and then I'm going to pop the root 2 up here. Okay, so that's one pair. We're bringing that new particle into C. It's going to interact with particle A. We've got that energy. It's also going to interact with particle B, and we need to figure out what that energy is too, because the symmetry is going to look the same, and all the particles are the same. So this is a nice simple case. D over root 2 as well. And now we're considering particles B and C here. And if I consider particle A and C and I consider particle B and C, then I'm considering all of the dynamics that particle C has to consider, right? This is the work necessary just to bring that particle C in. So the work done by you is going to be the sum of these two things. So that'll be 2 root 2 K Q squared over D. So this looks a little bit like the potential at point C, but it totally is not it, right? It's a different quantity. So notice that these are kind of subtle things. They seem subtle when you're first learning about potential. It's a fairly tricky quantity. So you just got to spend time with it, do lots of problems. Another approach to solving this one, I just want to show you a different way of doing that, would be looking at using this equation right here, potential as U over Q, solving that for the electric potential energy. Electric potential energy then would be the product of charge and potential. And if I apply that at point C, what that looks like then is the charge I'm bringing in, which is positive Q, multiplied by the potential at the point I'm bringing it to, or the elevation I'm bringing it to. And that is just V sub C, which we solved in part A, right? So that gives me Q multiplied by 2 root 2 KQ over D. And that's going to end up being the same thing as we just found here. So either of those approaches works there. Okay. When you think about this physically, I know this seems kind of nutty, but or different, I should say. But remember the gravitational analog. Always, always, always remember the gravitational analog. So when you're in this and looking at it, it's just like Q's and V's. What I want you to connect with is that what if instead of charge you had mass, right? And what if instead of potential you have elevation? And really, what you're looking for here, what you're trying to find here is you're trying to find um, the energy it takes to take a certain mass and lift it up a certain elevation. And you know that, right? You know all about that. So when you get lost in this, remember that it's really just about these forces that are happening in a field in exactly the way that they're happening in the gravitational field. And allow yourself to use gravitational field to help you think about it a little more kinesthetically, because you probably have that down pretty well now, gravitational field stuff.